Okay, everybody, let us finish off this quantum mechanics unit by taking a more general look at how light interacts with matter. So by the end of this lesson, we should be able to explain how atoms will absorb and emit light based on interactions with the electrons within there. So recall what we've learned so far about the photoelectric effect, that a photon of light, when it's incident on a particular atom, will be absorbed by an electron within the atom, which will cause the electron to be ejected from it because it's got enough energy to escape the pole of the nucleus. So the question here today is, more generally, what happens even if the electron energy is too low to cause the electron to be ejected? That's kind of sort of our question mark for today. So what we're studying here is something called an emission spectrum. If you take the light from a hot glowing gas, for example the neon in a neon sign, and you pass it through a prism or a diffraction grating to cause the colors to be separated, remember color is determined by wavelength, you don't get a continuous spectrum. What you're instead going to see is you're going to see some few very narrow, very well defined lines, which we might refer to as spectral lines. And so instead of getting a continuous spectrum, we would get a line spectrum, which might look something like this. So something that's relatively dense, like a light bulb filament, for example, when it glows, it's going to glow at a bunch of different colors. But something that's a little bit more diffuse, like a gas that's heated up, when it glows, it's only going to glow at a few very specific wavelengths of light. And so that's what the line spectrum over here is. Notice there's only a couple of lines that you actually see out of there. So remember that the wavelength of light is like what determines the color. And so what we're observing are unique wavelengths for any particular element or molecule. And we can use this as sort of an atomic fingerprint. This field of study would be called spectroscopy. I'll show you some examples kind of sort of at the end. What we want to do first is explain why something that is glowing may only glow at specific wavelengths rather than a range of wavelengths. And the feller who was able to do that for us was an Austrian by the name of Erwin Schrödinger, who is basically the father of what we today call quantum mechanics. And this was something that was first proposed in the year 1925 or so. Mr. Schrödinger, kind of like in the photoelectric effect, said that electrons and photons of light will interact with each other. So specifically, when light is emitted by something, it's because an electron is losing energy. So electrons lose energy, the photons gain those energies. Now the reason, according to Mr. Schrödinger, that we only see certain specific energies of photons is because the electrons that create the photons are only allowed to have certain specific energies, which is another way of saying that their energy is quantized. So what Schrödinger said was that the electrons within an atom are only allowed to have certain energies, meaning the photons that they create can only have certain specific energies. And then the next idea here is that electrons will spontaneously jump, quote-unquote jump, from high energy states to low energy states. We're going to refer to these as electron transitions or electron quantum jumps. And in the process, they release a photon of light, which carries away the energy that they lose in the process of going from one energy state to another. So if we kind of draw a picture of this, treating the electron classically, like as a particle, there's the nucleus of an atom, there's an electron moving with some velocity v, and then it loses some energy, again this happens spontaneously, and emits a photon to carry the energy away. So that's kind of sort of what the classical picture might look like. Of course, the classical picture is not going to be good enough. So a better way to represent this is with something called an energy level diagram. An energy level diagram basically represents the allowed energies for electrons in an atom, kind of sort of like rungs on a ladder. So if I kind of make up a hypothetical atom, not that this actually exists, but it'll be some easy numbers to work with, we might represent the energy levels as rungs on a ladder. So just like a real ladder, as we go down the ladder, the energy gets lower. The lowest possible energy state is referred to as the ground state. And this is where an electron would be most stable. States that above that are referred to, creatively enough, as excited states. We can label these things starting from the ground state with integer numbers like 1, 2, 3, 4, 5. We would give these the symbol n, and n represents the principal quantum number. You may have learned about the principal quantum number in chemistry way back in the day. The highest energy level is going to be assigned an energy of 0. Here we're going to use electron volts. So this top energy level has an energy of 0 EVs, and then I just made up some numbers for the ones going down. Now note that those energies are negative. And remember that they have to be negative because electric potential energy, the kind of energy we're talking about here, is 0 when the two things are infinitely far away. So an electron is infinitely far away from the nucleus of an atom, its energy would be 0. And so that position, that energy level, would represent the electron being infinitely far away from the atom. And remember that electrons will lose energy as they move closer to a positively charged nucleus, because they're attracted. So that's why those energies are negative. It's not so much important that we know what the actual energies are, because as it turns out, it's the energy differences that are important. That's kind of a general rule we've seen in physics over the last 2 years. So redrawing my diagram real quick. There's our ground state again. The big idea here is that quantum jumps, or transitions, occur when you have an electron that's been excited, like for example because the atom has been heated up. So there's where the excited electron would be, in one of those excited energy levels. And then it spontaneously loses energy by emitting a photon of light, which I might represent thusly. Now the energy of that photon is equal to the energy difference between the two energy levels from where the electron started to where it ended. So for instance, the energy of this photon would be 4 electron volts, because it started at -3 and it ended at -7, a difference of 4 eV. Now the electron can't exist anywhere in between. It can only go from -3 to -7, or -3 to -13. It can't exist anywhere in between. So we can only have electrons that match, photons that match that energy difference created. So again, these things are stable when they're in the ground state. So after that transition, sooner or later, it's going to spontaneously transition again. Create another photon. The energy of this photon will be like 6 eV, difference between 13 and 7. And once it's in the ground state, then it is stable. It's going to stay there if it has the choice. Of course, if this is still a hot sample of gas, the electron could be re-excited again, just due to heating, and then the whole process could be continuously happening. Electrons transition down, emit light, get transitioned back up again by some external energy source, and then the process repeats. Now this electron could have relaxed to the ground state in one step. Transition that would look like that, in which case it would have emitted a 10 electron volt photon. The actual sequence that happens, like for one given atom, is completely random and it can't be predicted. But remember, any sample that we're ever going to have, we're going to have something on the order of a mole of atoms, and so there's enough atoms that we just see continuously all the different photons that could be created being created. So what we would end up observing here is photons with 3 different energies: 4 electron volts, 6 electron volts, and 10 electron volts. But we would not observe anything else. Now, if we were to somehow get the electrons to be more excited and they started at the n equals 4 level, then we would see more photons. But we would still see only specific discrete energies for those photons. And so that kind of explains the emission spectrum. The absorption of light kind of works in the reverse of the process of emission. It might look kind of like this. If you take just white light, like from a light bulb, and you shine it on a cold sample of atoms, certain specific wavelengths of light are going to be absorbed. And if we take the light that emerges from the other side, and again separate it into a spectrum, we're going to notice lines that are missing. Like we'll see dark lines. And the picture is going to look something like that, where we would see one narrow little line, 2, 3, 4, so on and so forth, narrow lines of light that are missing. All the colors are there except those specific wavelengths. Those wavelengths were absorbed by our cold gas. And if you lay that picture side by side with an emission spectrum, you'll notice that the dark lines in the absorption spectrum line up exactly with the bright lines in the emission spectrum. So these wavelengths that were emitted before are the same as the wavelengths that are absorbed when you shine white light through the sample. And so let's see if we can kind of draw our energy level diagram picture and understand how that occurs. So the absorption occurs when you have an electron that's in the ground state. We might say that it is relaxed. So that would be a relaxed electron. And it encounters a photon of light whose energy exactly happens to match the energy difference between the ground state, which is where it starts at, and one of the excited states, where it could transition to. So for instance, if a 10 electron volt photon were incident on this particular atom, then that photon would be absorbed and the electron would become excited. It would gain a bunch of energy and it would move up, in this case, to the n equals 3 state. If we have an 8 electron volt photon incident on here, it would not be absorbed because it does not exactly match an allowed transition for the electron. The electron cannot exist at negative 8 eV. There's not a line there for it. There's not an energy state for it. And so an 8 eV photon would not be absorbed. So it's just going to go right through. So back over here, these lines represent those photons that exactly match those allowed transitions. And so out of the millions of different energies of photons that could be absorbed, only a couple actually get absorbed because they match exactly those energy transitions from one state to the other. So again, redraw my diagram. So in this case, our electron is now excited. If a 4 eV photon were to be incident on it at exactly the right moment, you could have the electron double absorb, kind of sort of if you will, more photons and be kicked up to even higher energy levels. Now again, they still have to match the energy difference between one level to the next. So 4 EVs would exactly match the difference between 3 and 7. So that thing could be absorbed. Keyword here being could. It is very statistically unlikely for that to actually happen. But it can happen in a large enough sample we would observe that it would happen. But again, it's very unlikely that would happen in any specific case. Okay, so hopefully we kind of understand the idea behind the energy level diagrams, and we can predict what photons would be absorbed and emitted It's kind of like a number game there. The next question is why can electrons only have specific energies? So answering the why question here. And so back in chemistry, you probably learned about the Bohr model of the atom, which was developed by a guy by the name of Niels Bohr in 1913. And so the model that you learned in chemistry was a classical treatment of the electron where we picture it as being a particle that is orbiting the nucleus, pulled inward by the electric force. Kind of like the moon orbits the Earth and is pulled inward by the force of gravity. What Mr. Bohr said, to add to that, is that electrons can only exist at specific distances from the nucleus. And those different distances corresponded with the different principal quantum numbers. That would be the values of n that we saw earlier. So like that inner circle would represent equal 1, the outer circle would represent n equals 2, and electrons can only exist exactly at those distances, not in between. So that when a photon of light is incident and absorbed, the electron moves further away from the nucleus, meaning it's gaining some energy. That also means that it's moving faster. And so you might kind of notice right away the problem with that. Why is the electron only restricted to a certain radius? It's like we really haven't answered the question any better than we had already before. Why is that true? So in order to explain this, we have to deviate again from classical behavior. We have to consider the fact that de Broglie thought that all things could act like a wave. And so we got to invoke wave-particle duality in order to explain why the electrons can only exist at specific distances from the nucleus. And so if we were to treat the electron as a wave, and kind of borrowing a picture of that, the circumference of the path that the electron follows as it travels around the nucleus has to be some integer number of wavelengths in order to actually exist as a wave. If it doesn't exist as an integer number of wavelengths, then it's going to destructively interfere with itself, which is bad, because that means that the electron wouldn't exist anymore, which is impossible. It's got to exist. We can't have energy just randomly destroyed. And so a couple of different pictures of allowed electron waves might look like that. And then the number of antinodes on those waves could correspond to the value of n, the principal quantum number again. And so we go from our model of the electron looking like this to our model of an atom looking more like this. So if you take the Schrödinger wave equation and you solve it for all possible orientations of the electron within the atom, then you get regions of space where the electrons could exist, and those regions of space are very well defined by wave mechanics. And so if you took AP chemistry, you may have learned the shapes of electron orbitals. Those are just the shapes of possible wavelength paths that you get when you use the Schrödinger equation, the wave function thing, in conjunction with the idea that electrons move around the atom as a wave. So kind of crazy, but we can only explain why electrons behave the way they do in an atom by assuming that they are waves. Okay, so armed with this knowledge, in studying emission spectrum, there's two super duper important things that we can do. So the study of spectra, again, which we call spectroscopy, is like super duper important. The first thing we can do, which what we focused on in this video, is understand the structure of atoms. And then later on we can understand the structure of molecules and more complicated things the same way, just by observing the light that is emitted from them when we make them glow. If you ever had your suitcase inspected going through the TSA checkpoints at the airport, They will take a cotton swab and wave it around your bag, inside of your bag, and then place it in an atomic absorption spectrum machine. And basically they're studying the light of whatever is coming off that cotton swab to determine what was actually inside your bag. And so it's really, really useful for figuring out what stuff is made out of and how it is actually made out of that. Another good example, this is how we know what stars are made out of. We can study the light from stars, and we can compare it to the light from similar elements or elements that we study here on Earth, and we can kind of play a little matching game. If we see lines that look like this coming from sunlight, then we know that helium must be present on the sun. So, fun fact, helium was actually discovered on the sun based on the bright line spectrum from the sun before it was discovered here on Earth. We saw lines in sunlight we hadn't discovered yet on Earth, and that's how we knew about helium. We can also use it to make cool signs, kind of like this neon sign right here. So we'll talk more about that when we get to class. Till then, ta-ta.